The main intrinsic factor that affects the chemical shift of a nucleus is the surrounding environment in the molecule that it's a part of. So the number and type of atoms that it's directly bonded to, or that are nearby within 3 to 4 bonds, say. Everything around the nucleus contributes to this environment, and this is what we call the chemical environment. There are usually many different chemical environments in an organic molecule, each with its own chemical shift. It's important to remember that each chemical environment in our molecule will give us one signal in our spectrum. So we can use this information to work out unknown structures. So for instance, if we have 4 signals in our proton and NMR spectrum, there must be 4 proton chemical environments in the molecule that we're taking the spectrum of. So if we look at the structure of the molecule that we're taking a spectrum of, we can predict how many chemical environments there are, and therefore how many signals we're expecting to see in the spectrum. So if we look at this molecule here, we have one chemical environment at the end of the chain where this CH3 is, these 3 protons here. We have these 2 protons, which are in the middle of the chain, they're a chemical environment. We have this proton on the benzene ring, which is at what's known as the ortho position, which is the position 1 around from this ethyl group. We have this proton here, which is ortho to the hydroxy group, and again, 1 around from that position. And we have the proton on the hydroxyl group itself. So we're expecting in total 1, 2, 3, 4, 5 proton chemical environments in this spectrum. And if we look at the spectrum, we can see there are 1, 2, 3, 4, 5 signals, not including the solvent signal, which, as we said in the previous video, was from the CHCl3 impurity in the NMR solvent that we're using. So why have I grouped these CH3 protons into the same chemical environment? Similarly, why have I grouped these protons on the CH2 into the same chemical environment? Well, this is to do with molecular symmetry. If there is a plane or an axis of symmetry in your molecule, everything on either side of that plane, or rotationally around that axis, will be in the same chemical environment. If we look at a model of our molecule, we can see actually there is a plane of symmetry all the way through the backbone of the molecule. Okay, all the way through here. And whenever you've got symmetry in a molecule, anything on one side of the plane of symmetry and anything on the other side of the plane of symmetry will be in the same chemical environment. So if we look at the CH2 first, we can see the plane of symmetry is all the way down the middle of the molecule here. So therefore, one of these nuclei is on either side of the plane of symmetry. So these 2 nuclei will be in the same chemical environment. The same is true of the CH3 group, although this is slightly more confusing because the plane of symmetry actually runs directly through this hydrogen atom here. So what you can also do is look for an axis of symmetry. And there is an axis of symmetry through this bond here. So if we rotate around the CH3 group, you can see that you can interchange the 3 nuclei through an axis of symmetry. Now, a good test for an axis of symmetry is if you were to secretly mark one of these nuclei and then go away and spin the axis around and then bring it back again, could you tell which nuclei you marked? If the answer is no, then that's an axis of symmetry, and all 3 of these nuclei are in the same chemical environment. Now, if nuclei are in the same chemical environment, like these CH2 nuclei are, and these CH3 nuclei are, they're what we call chemically equivalent. So this brings us on to our benzene ring, right? So we counted, when we were counting our chemical environments, these 2 as being in different chemical environments, because one was ortho to the ethyl group and one was ortho to the hydroxyl group. But what about the ones on the other side of the ring? Well, if we go back to our plane of symmetry here, we can see that this nucleus and this nucleus are on opposite sides of a plane of symmetry. So therefore this nucleus and this nucleus are in the same chemical environment. They are chemically equivalent. And the same is true of these 2 nuclei down here. So they're split by a plane of symmetry. So this nucleus and this nucleus are in the same chemical environment. Now the same principles apply to carbon NMR as to proton NMR. You're just looking at the carbon nuclei instead. So if we look at the structure of our molecule again, only now we're focusing on the carbons, how many carbon chemical environments are we expecting to see? Well, we've got 1 for the CH3 at the end, we've got 1 for this carbon that's part of the CH2, we've got 1 for this carbon that's the quaternary carbon connected to the benzene ring, we've got 1 for this one, 1 for this one, and 1 for this one that's connected to the OH. So in total we're expecting 1, 2, 3, 4, 5, 6 carbon chemical environments, which should give us 6 signals in our carbon NMR spectrum. And again, the principles of molecular symmetry apply as well. So this carbon and this carbon are in the same chemical environment, so we'll give 1 signal, and this carbon and this carbon are in the same chemical environment, so they'll give a different signal. So if we look at our spectrum, we've got 1, 2, 3, 4, 5, 6 signals, which matches the 6 carbon chemical environments that we're expecting.